Dissolving is when molecules separate from one another due to the pull of the solvent. Solvent is the part of the solution that the solute is placed. The solute is the thing that dissolves, the solvent dissolves it. And in dissolving, no bonds are actually breaking. It's just putting space between the molecules as they become solvated. Solvated means dissolved. So here we have sugar, or sucrose. Sucrose is a solid, turns into sucrose aqueous. Notice that there's space between them. So in this case, our solute would be the sucrose, and our solvent would be water. Because remember that aqueous means dissolved in water. So the sucrose stays together in the sense that the carbon, hydrogen, and oxygen bonds stay connected. Compared to dissociation, when it's going to separate into ions. So dissociation is the separation of an ionic solid into aqueous ions. So NaCl turns into sodium ion and chloride ion, which again will be in water. In the dissociated form, ionic compounds are able to react. When not dissolved or dissociated, the ions remain more attracted to each other, so it's hard for them to interact with a new molecule if it's brought in contact with the sodium chloride, for instance. Notice in the beaker, our sodium ions and chloride ions are separated. There's space between them. They'll be moving around. To figure out which salts actually break apart and dissolve or dissociate in water, we use solubility rules. You will have access to these solubility rules on a test or quiz. You just need to be able to read them. So how we read them is the top section means they're soluble. Soluble means that they're aqueous. They'll dissolve in water and break apart. While insoluble means that it's not going to dissolve, it's going to be a solid. So all of these are going to be soluble. If you notice, these are all the negative ions with the exception of the first two. The alkali metals are group 1A and then ammonium. So if you have one of these, it's going to be soluble unless it's paired with one of these. And then on the bottom, these are always insoluble unless it's paired with one of these. If you notice, for the exceptions, ammonium and alkali metals are the exception on all of these because alkali metals are always soluble, as are ammonium ions. So let's read our chart. So when looking at a compound, you're going to look at the second one, chloride. Here's chlorides. Chlorides are soluble unless it's paired with silver, mercury, or lead. Well, it's paired with one of those, so it's going to be not soluble. The next one, we don't have a rule for O, but we do have a rule for ammonium, or NH4. Ammonium ions are always soluble, no exception. So that's going to be soluble. So you can write NS and S, or you can say no, not soluble, yes, soluble. Let's look at two more. We have CO3. CO3 from your polyatomic ions is carbonate. And carbonates are insoluble unless it's with ammonium or an alkali metal. Well, calcium is in group 2A, not an alkali metal. It's an alkaline earth metal, so that would stay insoluble. The next one, CrO4, is chromate. And chromates are also insoluble unless they're with ammonium or an alkali metal. But potassium is in group 1A, so that one will be soluble. We also could have looked at the top and been like, oh, it starts with an alkali metal, it's going to be soluble. Go ahead and pause the video and try the next 3 on your own. So go to here, restart when you finish those 3. So nitrates, you should have said was yes, soluble. Iodine is soluble unless it's with one of these 3, and it wasn't. So that's a yes, soluble. And the last one, we have acetate. And acetates are soluble, no exception. So also soluble. Go ahead and do the next 3, restart when you have those done. So sulfate. Sulfates are soluble unless it's with one of these. Strontium is one of those, so that would be no, not soluble. Next, we can say phosphates are insoluble unless it's with one of these. But lithium is an alkali metal, so that would be a yes, it is soluble. And then the last one, sulfides are going to be insoluble unless it's with ammonium, an alkali metal, or one of these alkaline earth. It is one of those, so yes, that would be soluble. We're going to be using solubility in double replacement reactions. A double replacement reaction is when you have 2 compounds and they're going to basically switch partners or switch ions. It has the general formula of AB plus CD yields AD plus CB. The outside go together to form AD, and then the inside go together. The positive has to go with the negative, so CB. So positive, negative, positive, negative. We have 2 types, an acid-base reaction, where we have an acid reacting with a base to produce salt and water. You probably want to make note that an acid starts with hydrogen. We talked about that when we named acids, but just to refresh your memory, the one we haven't really talked about is bases. Bases are going to end in hydroxide for at least the reactions that we're going to be doing in this chapter. A salt is simply an ionic compound. A precipitation reaction is when 2 aqueous ions react to form a solid, which is the precipitate. We did talk about precipitation reactions early in the year, but now we're actually going to be predicting the products and figuring out who the precipitate will be. So looking at our first example, the first thing you want to do is list out your charges for everything. So looking on the periodic table, I see that barium's a +2, chlorine's a -1, potassium +1, and carbonate -2. If it helps, you can draw a line there just so you can visualize it a little bit better. So these outside ions are going to go together based on those charges. So barium's a +2, carbonate's a -2, so they cancel out. And then the middle 2 are going to go together. But the positive has to be written first. So it's going to be K, and then we've got +1, -1, so those also cancel out. Next, we're going to figure out if that's an acid-base or precipitation reaction. We can abbreviate acid-base to A/B, and precipitation can be PPT. Well, this isn't an acid and a base, so it must be a precipitation reaction. You can write that off to the side of your paper. If it's precipitation, you're going to look at these products and figure out which one is our solid. Okay, so we have carbonate. Here's our rule for carbonates. Carbonates are generally insoluble unless it's with ammonium or an alkali metal. It's not, so that must mean it's insoluble. Insoluble, remember we said, was going to be a solid. So that S stands for solid, not soluble. And then KCl, chlorides are going to be soluble unless it's with one of these, and it wasn't. So that's going to be aqueous. Finally, the last thing is we're going to balance it. On your practice, you'll balance it if it says to, otherwise you won't need to. We have 1 barium, 2 chlorines, 2 chlorines, 2 Ks, 2 Ks, 1 carbonate, 1 carbonate. So then this is my final answer. You can put ones in the other spots if you want. All right, let's look at these next two. So remember, first thing is we are writing our charges. It's important to write your charges because one of the most common things people mess up on is how the ions go back together. They don't put them together based on those charges, which causes them to miss it. So iron, we don't know its charge, but we know chlorine's a -1. -1 times 3 means that iron must be a +3. So then outside, inside, hydrogen is going with chlorine. We don't care that hydrogen has 2 and chlorine has 3 because it's only a 2 and a 3 because of what it's paired with. We're only looking at these charges, and the only way that a number is coming over is if it was part of a polyatomic ion. So H goes with Cl to form HCl. Plus, and then iron goes with sulfur. Sulfur was a 2, so we need to put that there. And then iron was a 3, so we're going to put that there. Then I figure out, is this an acid-base reaction or precipitation? I have an acid, but I don't have a base. So this is not an acid-base reaction. So this is precipitation. So I'm going to look at my solubility rules. Sulfides are insoluble unless it's with one of those. It's not with one of those. So that means that this is my solid. And it's not completely true right now, but chloride is up there. So this one is going to be aqueous. That's not the reason. We'll see the reason in a couple of days. But that's going to be our solid iron 3 sulfide. Okay, so now we can balance it. So go ahead and pause the video and balance your equation. Restart when you're done balancing. Okay, you should have had 3, 2, 6, 1. That's 6 hydrogens, 6 hydrogens, 3 sulfur, 3 sulfur, 2 iron, 2 iron, and 6 chlorine, 6 chlorine. Okay, let's look at the next one. So again, we're going to write our reactants charges. Break it apart. Outside are going together. So calcium is going to go with chlorine, and they go together like that. And then H is going to go with OH. So it goes together like so. We can leave it as HOH, but HOH makes H2O. Then we're going to identify what our type of reaction it is. This ends in OH, so that is a base. This starts with hydrogen, so it's an acid. So this is an acid-base reaction. If you wanted to add your state symbols, water is going to be technically a liquid. And we could look at the chlorine. Chlorine is soluble unless it's with one of those. It's not. So that's aqueous. Notice we don't have a solid in this case because this isn't a precipitation reaction. You sometimes can make a solid on an acid-base reaction, but the characteristic of an acid-base reaction is you're always going to have water as one of your products. All right, go ahead and pause the video and write your reactants for D. Restart when you have your reactants. So potassium was a +1, chromate was a -2, And then tin is a 2 and fluoride is a -1. So we've got that. We have all our charges listed above, so I don't need to rewrite them. But potassium is going to go with fluoride, and tin is going to go with chromate. So go ahead and pause the video and write your products with the correct charges or with the correct subscripts. Restart when you're done. So potassium went with fluoride, so K goes with F. Those cancel out. And tin should go with chromate, so SnCrO4. Just FYI, if you'd written your products like this, that also is correct. What would be incorrect is if you put FK plus CrO4Sn. You have to write the positive one first, so that would not be correct. So then, if we were figuring out which type of reaction this is, we don't have an acid, we don't have a base, so this must be precipitation. So figure out which of our products is a precipitate. Restart when you've got your precipitate. Well, potassium is group 1A, so we know that it's going to be soluble. Always double check that the second one is as well. Sometimes they're both aqueous, and then we have a no reaction. So chromates are insoluble, and that's not one of the exceptions, so that's my solid. Okay, pause the video and write your reactants for E. So they should have went together like that. Go ahead and pause the video and now write your products. Restart when you have your products. So one of my products was H2O because H goes with OH to make H2O. And then barium should go with sulfate in a 1-to-1 ratio. Next, figure out which type of reaction this is. Restart when you're done. You said acid-base, you're correct. This one starts with H, so it's an acid. This one is my base. This one is liquid. And barium sulfate, if you look at the solubility rules, sulfates are soluble unless it's one of these. And so we actually do have a precipitate in this case, but it's still classified as an acid-base reaction. We didn't balance this one, so we need a 2 in front, and we actually didn't balance the other one. So we just need a 2 in front of KF if you want to have it balanced. All right, go ahead and write your reactants for this last one. Restart when you're done. So ammonium is an H4, and we need 3 of them to cancel out phosphate's charge. Silver and nitrate cancel. Go ahead and pause the video and do your products. Restart when you're done. So ammonium is going to go with nitrate in a 1-to-1 ratio. And silver, we need 3 of that to cancel out phosphate's charge. So which type of reaction is this? You said precipitate, you're correct. And so now add your state symbols to your 2 products. Restart when you're done. So ammonium is soluble, no exception, so that should have been aqueous. And phosphates are insoluble unless it's one of those few exceptions, so that was your solid.